If you wanted to uncover the secrets of the universe for yourself, you'd simply need to ask the right questions until the universe responds in a way you understand. Imagine you could peer through everyday objects to see what they are truly made of. If you looked closely at the arm of a chair, you would find it's made of atoms. Zoom in further, and you'd discover these atoms contain subatomic particles: protons, neutrons, and electrons. Go even deeper, and you'll see that protons and neutrons are made of quarks. These layers represent how physicists understand the universe by breaking everything down into smaller pieces, a method called reductionism, a scientific approach that breaks down complex systems or phenomena into their simpler, more fundamental parts to better understand how they work. The idea is that by studying these basic components and their interactions, one can explain the behavior and properties of the entire system. Instead of focusing on the tiny details, why don't we take a broader view? By doing this, we might realize that everything, including space and time, emerges from a unified whole. While this may sound like philosophy or mysticism, it is actually based on applying quantum mechanics to the entire universe. This reveals that the universe isn't made up of separate parts, but is a single quantum entity. This may sound a bit implausible, but hear me out. Most of us here already know what quantum mechanics is all about, but for those who don't, let me give a simple analogy for you to get it. Imagine you're in a room with a light switch. In the everyday world, that switch is either on or off, just like a light bulb is either lit or not. But in the quantum world, it's as if the switch can be both on and off at the same time, until you actually look at it. It's like the light is in a weird state of kind of on and kind of off, until you flip the switch or check it out. This strange behavior is what quantum mechanics is all about. Things can exist in multiple states at once, and they only choose a state when we observe them. It's like the universe plays a game of probabilities until we make it reveal its hand. Now, you might be thinking, how does this relate to the real world? Well, quantum mechanics isn't just some abstract idea. It's the foundation of how everything around us works, from the smallest particles to the entire universe. In the everyday world, we don't notice these strange quantum effects because they mostly happen at incredibly tiny scales, like inside atoms. But those tiny scales make up everything we see, touch, and interact with. The phone in your hand, the chair you're sitting on, even the cells in your body, they all operate under these quantum rules. When you look around, you see solid objects in definite positions. But at the quantum level, particles are constantly shifting, existing in multiple places at once, and only settling into a single state when measured or observed. This is why quantum mechanics is so mind-bending. It challenges our usual ideas about reality, showing us that at the deepest level, the universe is far stranger and more connected than we might think. So, while you might not see quantum effects in your day-to-day life, they're there, shaping everything around you in ways that are both subtle and profound. And understanding these principles gives us insights into the true nature of reality, where the rules aren't as straightforward as they seem. For nearly a century, physicists have been trying to uncover the most basic building blocks of reality, often describing systems without fully grasping what's happening within them. Take the 1930s, for instance, when Enrico Fermi figured out how a neutron decays into a proton and releases an electron, a process known as beta decay. Fermi's understanding was based solely on the electrons, protons, and neutrons involved. It wasn't until decades later, with the discovery of the W and Z bosons, that scientists realized there was a deeper, more intricate layer of interactions happening on an even smaller scale. From today's viewpoint, Fermi's description serves as a classic example of an effective field theory, EFT. This is a mathematical framework that lets us break down reality into different size scales and study each one separately. It's like a set of Russian matryoshka dolls. You can understand the outer doll without needing to know what's inside. Similarly, in physics, we can grasp certain phenomena without fully understanding the deeper layers that might be hidden within. Essentially, EFTs allow us to understand and work with parts of the universe at different scales, different sizes and energies, without needing to understand the full picture all at once. As physicist Cliff Burgess puts it, everything is an EFT. The universe operates on various scales, and each scale corresponds to a different level of energy. The largest scales, like galaxies and the observable universe, are associated with the lowest energies. These cosmic structures are governed primarily by gravity, which is the weakest of the four fundamental forces. The energy associated with these scales is relatively low, as the interactions between objects are dominated by long-range gravitational forces. Conversely, the smallest components of reality, such as subatomic particles, are linked to the highest energies. At this level, we see a significant increase in energy. The electromagnetic force dominates here, governing the interactions between electrons and atomic nuclei. The energies associated with phenomena at this scale are the highest we can observe or create in particle accelerators. This inverse relationship between scale and energy is a crucial aspect of our understanding of the universe. For example, when Fermi described how a neutron decays into a proton and an electron, Fermi didn't have the powerful tools like the Large Hadron Collider that we have today, so he couldn't detect the smaller scale reality of particles like the W boson that mediates this interaction. His description was effective for his time, but was an approximation of a more fundamental theory. Today, we understand that the standard model of particle physics, our best theory describing the basic building blocks of matter, is itself an EFT. It successfully explains many aspects of particle physics, but doesn't include gravity, the mysterious dark matter, or fully account for the peculiar masses of neutrinos. This realization shows us that the standard model, like Fermi's earlier work, is only part of a bigger picture. As useful as EFTs are, they can sometimes obscure a deeper understanding of the universe. For instance, when physicists try to calculate the mass of particles like the Higgs boson using the standard model, they run into what's called the fine-tuning problem. In quantum mechanics, particles can briefly transform into short-lived virtual particles before returning to their original state. These virtual particles contribute to a particle's mass, but calculating this contribution depends on the energy scales we're working within. The problem arises because, according to the theory, the Higgs boson's mass should be much larger than what we actually observe. This discrepancy is as unlikely as a pencil perfectly balancing on its tip, something known as fine-tuning. To solve these puzzles, physicists have proposed various theories, such as supersymmetry or the existence of extra dimensions. These ideas suggest that new particles or dimensions could be responsible for balancing out the quantum fluctuations that affect particle masses. However, experiments at the Large Hadron Collider have yet to find evidence supporting these theories, leading to what some describe as a crisis in particle physics. This has prompted some physicists to explore more radical approaches. Instead of viewing the different scales of the universe, like the smallest particles and the largest cosmic structures, as independent, they are beginning to treat them as interconnected. The idea that the universe can be understood through its smallest components, with each tiny part reflecting the whole, creates a sense of coherence across different levels of observation. This perspective suggests that by examining the fundamental elements of the universe, we can uncover patterns and connections that unify the smallest details with the larger structure. This approach challenges the traditional idea of reducing everything to smaller and smaller parts to understand the universe. Instead, It suggests that these parts might all influence each other in ways we don't yet fully understand. We'll talk about this later in the video. To illustrate this, think of a rainbow. The visible colors represent the part of the electromagnetic spectrum that we can see. Beyond the violet end lies the ultraviolet, UV region, associated with higher energies and smaller scales, like those where quantum gravity might come into play. On the other end, beyond red, lies the infrared, IR region, linked to larger scales and lower energies, like those associated with the vast distances in the universe. Each color in the rainbow is distinct, yet they all blend seamlessly into one continuous spectrum, illustrating the unity and coherence of light. Similarly, the different scales of the universe, from the tiniest particles to the vast cosmic structures, are interconnected parts of a unified whole. Just as the rainbow's colors are manifestations of the same underlying phenomenon of light, the various components of the universe reflect a deeper, interconnected reality, suggesting a cohesive understanding of the cosmos. Physicists have long believed that the Standard Model breaks down at the Planck scale, but recent research suggests that there might also be a lower limit, where gravity takes over at very large distances or low energies, hinting at a connection between these vastly different scales, a phenomenon known as UV-IR mixing, a situation where high energy, ultraviolet, and low energy, infrared effects, become unexpectedly interconnected. It challenges the conventional separation between these energy scales. This idea of UV-IR mixing suggests that the smallest and largest scales of the universe might not be independent of each other, but are instead deeply connected. Some theorists even propose that quantum entanglement, where particles are linked in such a way that the state of one immediately influences the state of another, regardless of distance, could be the key to understanding this connection. If true, this could mean that what happens at the tiniest scales of the universe could influence the largest, and vice versa. This brings us back to the idea of the universe as a single quantum object. At the most fundamental level, the idea that the universe is a single quantum object challenges our conventional understanding of reality. This perspective emerges from the principles of quantum mechanics, where the distinctions between separate objects, particles, and even forces start to blur. When we consider the universe in its entirety, we're confronted with a deeply interconnected, holistic reality that defies classical intuitions. One of the cornerstones of quantum mechanics that supports this idea is quantum entanglement. When two or more particles become entangled, their properties become so deeply linked that the state of one particle instantly influences the state of the other, regardless of the distance between them. This phenomenon suggests that the separation between objects is not as clear-cut as it appears in our everyday experience. Albert Einstein famously referred to it as spooky action at a distance. If quantum entanglement can connect particles across vast distances, it might also link different energy scales, from the Planck scale to the cosmic scale. This would mean that the universe isn't made up of independent parts, but is instead a single, indivisible entity. In the words of quantum pioneer David Bohm, the universe could be seen as a single, indivisible unit, with everything in existence encoded in a universal wave function, a mathematical description of a single, entangled state. This perspective challenges the way we've traditionally understood the cosmos. It suggests that instead of focusing on smaller and smaller pieces to understand reality, we need to consider the universe as a whole, where every part influences every other part. This holistic view could revolutionize our understanding of fundamental physics and bring us closer to a more complete picture of how the universe is put together. In this view, the universe is not a collection of isolated parts, but a single unified system where everything is interconnected. Every part of the universe, from the smallest subatomic particle to the largest galaxy, is part of this interconnected whole. This entangled web forms the fabric of reality, binding the cosmos together in ways that are beyond our conventional understanding. In classical physics, we draw clear lines between objects and forces. We talk about space as a vast, empty stage on which matter and energy perform their dance. Time is seen as a linear progression, moving forward from the past to the future. But when we view the universe as a single quantum object, these distinctions begin to blur. Space and time themselves become emergent properties, not fundamental aspects of reality, but results of the underlying quantum state of the universe. In this view, space and time are like the surface of the ocean. What we see and experience in our everyday lives are just the ripples on the surface, while the deeper reality lies beneath. Imagine a wave on the ocean. To an observer on the shore, the wave appears as a distinct, moving object with a clear beginning and end. But we know that the wave is not a separate entity. It's simply a manifestation of the movement of water molecules within the ocean. Similarly, the objects and events we observe in the universe are like waves on the surface of a deeper quantum sea. They are not isolated entities, but expressions of the underlying quantum field that connects everything. Now, just as the wave on the ocean is an expression of the water beneath, quantum mechanics introduces us to another type of wave, one that's not made of water or any physical substance, but of probabilities and potential outcomes. This is where the concept of the wave function comes into play. In quantum mechanics, the wave function is a mathematical function that describes the probabilities of a quantum system's various possible states. When we extend this concept to the universe as a whole, we arrive at the idea of the wave function of the universe. This wave function doesn't just describe a single particle or system. It encapsulates the totality of all possible states of the universe. In this view, the universe is like a blend of all possible outcomes, with every potential state existing at the same time until it's observed or measured. This idea brings us to a powerful conclusion. The entire universe is a single quantum entity where all possibilities are connected and depend on each other. Seeing the universe as one quantum object changes how we think about reality. It suggests that the separations we see are just an illusion, a useful one for everyday life, but an illusion nonetheless. At the deepest level, there's no true division, no separate objects or events. Everything is part of one continuous, interconnected whole. This idea is further supported by the concept of non-locality in quantum mechanics. The concept of non-locality in quantum mechanics further reinforces the idea of the universe as a single quantum object. Non-locality refers to the phenomenon where events occurring at one location can instantaneously influence events at another location, without any apparent connection through space. This challenges our classical notion of locality, where objects and events are only influenced by their immediate surroundings. If non-locality applies universally, then the entire cosmos is interconnected in a way that transcends the limits of space and time. Every point in the universe is potentially connected to every other point, not through the familiar fabric of space, but through a deeper quantum reality. This suggests that space itself might be an emergent property of this underlying quantum entanglement, rather than a fundamental aspect of reality. Non-locality is not just a theoretical curiosity. It has been experimentally verified in numerous studies. The fact that particles can be entangled and influence each other instantaneously across great distances suggests that the universe is not composed of isolated, independent parts, but is instead a single, interconnected quantum system. It means that the universe does not operate according to the classical deterministic laws we once thought it did, but instead follows a deeper, non-local quantum logic. Taking the concept even further, some interpretations of quantum mechanics propose a connection between the universe and consciousness. The idea here is that the act of observation or measurement is what causes the wave function to collapse, selecting a single outcome from the superposition of possibilities. If the universe is a single quantum object, then consciousness itself might be intertwined with the quantum state of the universe. But the quantum view goes even further. In this fabric, every part of the universe is aware of every other part. This is not consciousness in the human sense, but a kind of quantum awareness where the state of one part of the universe is intimately linked with the state of another. This is the essence of entanglement on a universal scale. It means that the universe behaves as a single entity, with its parts influencing each other in ways that transcend the limitations of space and time. The universe, as a singular quantum object, might be as much a product of consciousness as consciousness is a product of the universe. This idea is speculative, but it opens up new avenues for understanding the relationship between mind, matter, and the cosmos. This idea draws on the concept of panpsychism, the belief that consciousness is a fundamental aspect of all matter, and that even the most basic particles possess a rudimentary form of awareness. While this idea is highly speculative and remains on the fringes of scientific thought, it challenges the conventional separation between mind and matter, suggesting that consciousness is not confined to biological organisms, but is a fundamental feature of the universe itself. In this view, the universe is not a cold, lifeless machine, but a dynamic, self-organizing system that evolves and adapts in response to its internal quantum interactions. This perspective aligns with some interpretations of quantum mechanics, which suggest that the act of observation plays a crucial role in shaping reality. If the universe is a living, conscious system, then the distinction between observer and observed becomes meaningless, as both are part of the same quantum process. Building on this perspective, if future experiments confirm the ideas of UV-IR mixing and the role of quantum entanglement in connecting different scales, it would fundamentally alter our conception of the universe. We would see that the universe, in its entirety, is not just a collection of separate objects and forces, but is a single, interconnected quantum entity. This understanding would not only help us solve some of the biggest puzzles in physics, such as the nature of dark energy and the mass of neutrinos, but it would also offer a new way of thinking about the cosmos, one that views the universe as a unified whole, where every part is intimately connected to every other part. All we've talked about in this video may seem kind of weird, but that's because we're pushing the boundaries of what we know and what we think we know about the universe. It's not just about quirky quantum mechanics or abstract theories. It's about challenging our most fundamental assumptions. What if the separations we see between objects, forces, and even ourselves are just illusions? What if, at the deepest level, everything is connected in ways that defy our conventional understanding? The universe as a single quantum entity might sound strange, but it could hold the key to unlocking some of the greatest mysteries in science. And perhaps, more importantly, it invites us to see reality in a new light, one where everything is part of a unified whole, intimately connected, and constantly influencing each other in ways that are both profound and beautiful. So, while it might feel a bit out there, this perspective might just bring us closer to the truth about our place in the cosmos.